Welcome to my sixth and final lab about magnetic molasses. Here's the table of contents. So in this lab, some key concepts that we're going to need to understand in addition to normal rules of magnetism are Faraday's law, that a changing magnetic flux through a coil induces an electric current through that coil, which is Faraday's law, and Lenz's law, that the electric current will oppose the direction of the changing flux. Essentially, the system is trying to return to equilibrium, and the changing magnetic field is going to induce a current inside of the wire, which is then going to induce a magnetic field in the opposite direction. So we're going to observe this effect using the position and velocity update formulae for a falling magnet, which will have a changing flux as it falls through a tube of wire. So the goals are to measure the time it takes for a magnet of a known moment, which we found in lab 4, to travel through an aluminum tube. We need to simulate the changing magnetic field and force of the aluminum tube. And assuming the aluminum tube is a series of solenoids, solenoid wire loops, that is, we need to predict the time it will take for this magnet to fall. So the purpose is to demonstrate the power of Faraday's and Lenz's law in conjunction with one another. And we need to find what is the fall time, t, and how does the simulation compare to real life? Does the solenoid sufficiently cause the falling magnet to break and fall slower? Experimentally, we found that the magnetic moment was 2.9 ampere meters squared. The tube length is 0.3 meters. The foil width is 0.01 meters. And the inner tube radius is 0.02 meters. So it's a very long tube. The magnetic mass is also 0.025 kilograms, which is important for understanding the effect of gravity in the situation. Qualitatively, when we did the experiment in real life, we found that the magnet really did fall more slowly as the magnetic laws predicted. Quantitatively, we found that the average fall time was 0.96 seconds, and that's averaged over 5 trials. However, through the simulation, the simulated fall time was 0.23 seconds. And here you can see that the velocity changes at a constant rate, which we would see through gravity, not through the laws of magnetism of Faraday and Lenz. Here's the experiment. It's 3, 4, and one more time, 5. And here's the results of those here, which we used after the video through frame-by-frame analysis. So here's the code. The code's very complicated, and it's essentially representing these formula, which is that the EMF, the voltage, should reflect the number of solenoids, the changing flux, and the change in time. This flux is going to be the magnetic field multiplied by the area of the flux, and essentially it's going to be a cross product. We also have the force from the magnetic field on the magnet. The time in the tube was 0.233 seconds by simulation, and the experiment versus simulation difference is about 75.7% error, which is an incredible difference. One of the main things that we can see here is that there is a linear graph starting at 0, and that is not something that should be happening. That is an indication that only gravity was taken into effect, meaning that somewhere in the code there is a mistake. There is something not taking the magnetic force into account at all. Experimentally, the laws of magnetism slow down the magnet as it falls through the foil and induces a field. This is what we saw in real life through the 0.96 seconds, and the simulation is radically different because of this. The simulated drop time of the magnet is not even comparable. Why? And does it contradict Faraday or Lenz? In my opinion, no. In real life, we saw that Faraday or Lenz, their laws really did come to fruition. If those laws had not been in effect, the magnet would have fallen over 0.2 seconds, which it clearly didn't in real life. So some sources of distortion were nearby electronics and magnets, contact between the foil and the table, all of which could have changed the current in the foil and therefore the magnetic force in real life. Also, there could be some human error with timing and the frame-by-frame analysis and standard measurement errors. However, it is the opinion of the lab group that the main error here is through the simulation. Are all the conditions accounted for? Is there an error somewhere in the code? Almost definitely. And why is the graph linear? Because it's not taking the magnetic force into account, which should make the graph a lot less steep toward the end, frankly. And in the code, we see that magnetism induces almost no force, which is not reality. So what if the resistance of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? Essentially, with lower resistance in the coiled wire, induced EMF voltage remains the same according to Faraday's laws. However, the current will increase according to Ohm's law. The greater current will then have a greater inverse magnetic field on the falling magnet, and then the force will be greater as a result, slowing it down even more. So more radical difference. And then what if holes or slots were cut into the tube at random places? Any holes, slots, or cuts in the tube would simply result in a lower number of rings in the model. They would be incomplete rings. They would have less area. There would just be a smaller capital N value for the solenoid in general. These rings also don't impact the flux or the force themselves, as they are not in the right orientation relative to the falling magnet to have any flux whatsoever. They are not perpendicular to the plane of the holes. So as the magnet falls and its magnetic moment points down, they have no effect on the falling of the magnet other than less of the solenoid in general, which is a very small effect. And that's it. Thank you.